Your brain isn't designed to make you happy, it's designed to keep you alive. And those are two completely different things. Every time you sit down to do the work that matters, something invisible pulls you away. You reach for your phone, you open a new tab, you find a reason to start tomorrow instead, and you tell yourself it's laziness, or a lack of willpower, or that you just don't want it badly enough. But what if none of that is true? What if your brain is doing exactly what it evolved to do, and the real problem is that nobody ever taught you how the machinery actually works? Because here's what almost nobody realizes. Self-sabotage isn't a character flaw. It's a neurological feature. And once you understand the wiring, you can stop fighting yourself and start working with your own biology instead of against it. In 1999, psychologist Daniel Wegner and his colleagues at Harvard conducted a deceptively simple experiment. They told participants, "Don't think about a white bear." For the next 5 minutes, every time the image of a white bear popped into their minds, they had to ring a bell. The bells rang constantly. Then Wegner gave them a second task. Think about a white bear as much as you want. A separate group who had never been told to suppress the thought did the same. The first group, the ones who had spent 5 minutes actively pushing the white bear away, thought about it significantly more than the second group. This is the ironic process theory. The harder you try not to think about something, the more your brain fixates on it. But here's the deeper mechanism. Your brain has two systems running in parallel. System 1 is fast, automatic, emotional. It lives in the limbic system, the amygdala, the nucleus accumbens, the ancient structures that kept your ancestors alive on the savannah. System 2 is slow, deliberate, logical. It lives in the prefrontal cortex, the thin layer of neural tissue behind your forehead that evolved much more recently. When you tell yourself don't procrastinate, System 2 is speaking. But System 1 doesn't process negation, it only hears procrastinate. And because System 1 is faster, stronger, and more deeply wired into your reward circuitry, it usually wins. A young entrepreneur named Sarah built a successful consulting business from nothing. She was disciplined, focused, relentless, but every time her company reached a new revenue milestone, she would mysteriously stop returning client emails. She would miss deadlines she had never missed before. She would find herself reorganizing her desk for hours instead of closing deals. She wasn't lazy, she was terrified. Her brain had learned somewhere in childhood that standing out meant becoming a target. So every time she succeeded, System 1 pulled the emergency brake, not because it wanted her to fail, but because it genuinely believed success was dangerous. Your brain doesn't sabotage you because it's cruel. It sabotages you because it's trying to protect you from a threat that no longer exists. In the 1950s, neuroscientists James Olds and Peter Milner inserted electrodes into the brains of rats. When the rats pressed a lever, they received a small electrical stimulation to a region called the nucleus accumbens. The rats stopped eating, stopped sleeping, stopped everything. They pressed the lever thousands of times per hour until they collapsed from exhaustion. That region is the heart of your dopamine system. And here's what modern neuroscience has revealed. Dopamine isn't the chemical of pleasure, it's the chemical of anticipation, of wanting, of pursuit. When you scroll through social media, your brain releases dopamine not because you're satisfied, but because you're searching for the next interesting thing. Each swipe is a tiny gamble. Each notification is a variable reward. And your dopamine system is exquisitely sensitive to variable rewards, far more than to predictable ones. This is why your email inbox feels irresistible. But your brain has a second dopamine pathway most people never hear about, the tonic versus phasic distinction. Tonic dopamine is your baseline, the slow, steady hum that keeps you motivated for long-term goals. Phasic dopamine is the spike, the sharp burst you get from novelty, from sugar, from a like on your post. Modern life is a phasic dopamine casino. Every app is engineered to spike your dopamine, which means your baseline slowly drops. You need more and more stimulation just to feel normal. And the long-term projects, writing the book, building the business, learning the skill, they run on tonic dopamine, so they feel gray, boring, impossible to start. James Clear, in his research on atomic habits, noticed something fascinating about elite performers. They don't rely on motivation. They design their environments so that the right action is the path of least resistance. But there's a neuroscience layer he rarely discusses. When you repeat a behavior in the same context, Your striatum, the habit center of your brain, starts encoding it as an automatic script. The prefrontal cortex, which consumes enormous energy, gradually disengages. This is why habits feel effortless once established, and why breaking bad habits feels like you're fighting yourself, because you literally are. You're trying to override a neural script with conscious willpower, which is like trying to stop a train by pushing against it. The solution isn't to push harder, it's to change the tracks. Your prefrontal cortex is magnificent. It's the seat of planning, impulse control, abstract reasoning, and long-term decision-making. It's also incredibly fragile. Neuroscientist Amy Arnsten at Yale has spent decades studying how stress affects the prefrontal cortex. Under mild stress, it actually performs better. This is the well-known Yerkes-Dodson curve. But under chronic or acute stress, something remarkable happens. The prefrontal cortex shuts down, literally. The neurons stop firing properly. Control shifts to the more primitive subcortical structures. The amygdala, the habit circuits, the survival instincts. This is why you make terrible decisions when you're anxious. Why you eat the junk food, skip the gym, send the angry email. Your prefrontal cortex isn't weak. It's offline. And here's where everything changes. Most people try to build discipline by adding more stress. They set punishing schedules. They berate themselves for failure. They rely on guilt and shame as motivators. But guilt and shame activate the same stress circuits that shut down the prefrontal cortex. So the more you beat yourself up, the less access you have to the very part of your brain you need to change. A study by Royce and Pykill in 2013 found that self-forgiveness, not self-criticism, was the strongest predictor of reduced future procrastination. Not because forgiveness feels good, but because it lowers cortisol. It brings the prefrontal cortex back online. Think of it this way: your prefrontal cortex is like a high-performance engine that only runs on clean fuel. Stress is contaminated gasoline. It might get you moving for a moment, but it destroys the machinery. In 1974, psychologists Amos Tversky and Daniel Kahneman published a paper that would eventually win a Nobel Prize. They described something they called cognitive biases, systematic errors in thinking that distort our decisions. But what they didn't fully explain was the neuroscience underneath. Your brain is a prediction machine. It doesn't perceive reality directly. It generates a model of what it expects to see, then compares that model to sensory input. When the match is close, everything feels smooth. When there's a mismatch, your brain works hard to update the model. But updating models is metabolically expensive, so your brain takes shortcuts. One of the most dangerous shortcuts is confirmation bias. Your brain prioritizes information that confirms what it already believes, not because it's stubborn, but because it's efficient. Believing new things requires neuroplasticity, the physical rewiring of synaptic connections, and neuroplasticity requires resources, attention, and time. This is why you can read 10 books about habits and still not change. Your brain isn't resisting the information. It's filtering it through existing neural pathways. The knowledge enters, but it doesn't restructure the circuitry. Neuroplasticity is real, but it's slower than most people think. In the 1990s, researcher Michael Merzenich demonstrated that when monkeys practiced a specific tactile task, the corresponding brain maps expanded significantly. But the key detail, the expansion required thousands of repetitions over weeks. Not days, not hours, weeks. Your brain is doing something you don't even notice. It's treating every new behavior as a threat to energy conservation. Until a new neural pathway is myelinated, wrapped in the fatty insulation that speeds up electrical signals, it will always feel harder than the old pathway. This is why change feels like swimming upstream, because neurologically, it is. Antonio Damasio, a neuroscientist at USC, studied patients with damage to their ventromedial prefrontal cortex. These patients could solve logic puzzles perfectly. They could describe the consequences of decisions with crystalline clarity, but they couldn't make simple choices. Should I have the fish or the chicken? They would sit for hours, paralyzed. Damasio proposed the somatic marker hypothesis. Emotions aren't obstacles to good decisions. They are essential data. Your body generates subtle feeling states, somatic markers, that tag options as good or bad before you consciously think about them. Without this emotional tagging, pure reason is paralyzed. But here's the problem: your emotional ledger is written in childhood. Early experiences create powerful somatic markers that persist for decades. If failure was punished harshly, your body tags risk with dread. If success was ignored, your body tags achievement with emptiness. You can intellectually know that starting a business is a good idea, but if your emotional ledger associates visibility with danger, you'll find ways to disappear just as things get interesting. Mel Robbins often talks about the 5-second rule, counting down 5, 4, 3, 2, 1, to interrupt hesitation. Hesitation gives your amygdala time to activate. The countdown engages your prefrontal cortex before the emotional alarm bells ring. It's not magic, it's a race between two neural systems, and you're giving the slower one a head start. But the deeper work is updating the emotional ledger itself. This requires what psychologists call exposure with response prevention, deliberately approaching what you fear without engaging in the safety behavior. Each time you do this, your amygdala learns, slowly, grudgingly, that the threat is outdated. The somatic marker fades. The ledger rewrites itself. Charles Duhigg, in his exploration of habit science, described the habit loop: cue, routine, reward. But the neuroscience goes deeper. In your basal ganglia, there's a structure called the striatum. It contains two parallel pathways, the go pathway and the no-go pathway. The go pathway releases dopamine when you perform a behavior that leads to reward. The no-go pathway suppresses behaviors that lead to punishment. In a healthy brain, these pathways are balanced. But chronic stress, sleep deprivation, and poor nutrition shift this balance. The go pathway becomes hypersensitive to immediate rewards. The no-go pathway weakens. This is why willpower fails when you're tired. It's not a moral failing, it's neurochemistry. Andrew Huberman's lab at Stanford has done fascinating work on what he calls limbic friction, the resistance you feel when trying to do something difficult but valuable. Huberman points out that this friction isn't uniform, it's highest at the transition point, the moment before you start. Once a behavior begins, the friction drops dramatically. This has profound implications. The most important part of any habit isn't the middle, it's the first 10 seconds. If you can reduce the friction of starting, laying out your gym clothes the night before, opening the document before you go to bed, putting the guitar in the middle of the room, you bypass the no-go pathway before it can activate.